Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to apply Gauss's law in cases that has spherical symmetry. So in this example, imagine we've got a total charge Q distributed uniformly throughout the volume of the sphere of radius r. And what we're going to do here is we're going to kind of investigate what the electric fields look like both inside and outside that sphere. Now first of all, let's talk about, why would there be an electric field in the sphere? All right, imagine placing a positive charge right there, right at the center, and ask yourself what you believe the net force on it would be. So if you think about that for a moment and look at the symmetry of the problem, hopefully it's fairly clear that the net force on that particle would most likely be zero, and hence there'd be no electric field at the center. Right, now imagine putting that particle maybe here, and imagine that being right on the x-axis. Now, notice that the problem is symmetrical if we stay close to it, but when we get a ways out, you see how there's charge over on the left and there's no charge over here to, for lack of a better way to put it, to counteract it. So now we have an imbalance in charge. So this particle would experience a force to the right, and therefore at this point right here there would be an electric field which would point to the right if we're right on that x-axis. So what we want to be able to do here is we want to be able to write an expression for what that electric field looks like. What I want some function for the electric field as it varies with the radius of this sphere. All right, so again, here's an example where we would use Gauss's law. And in order to use Gauss's law, the first step is always to draw a Gaussian surface. Now I'm going to go ahead and create my surface, over here and basically move it into that sphere. Normally what you would do, if you're working with these problems at home, is you would draw that surface right on your paper. I'm going to go ahead and kind of create it outside of here and move it in there. I always put my Gaussian surfaces in green. G for green and G for Gaussian, I guess. Alright, so we have a Gaussian surface. It has a certain radius. Now that's going to be little r. Little r in this example is going to be the radius of my Gaussian surface. Alright, now what I'm going to do is I'm going to move that surface inside of this charge configuration. Now, what I would do, if this were your homework, you would draw it here. So there's my Gaussian surface, and before I do anything else, there's a very important point that needs to be made. Look at that surface right now and consider the amount of charge inside of it, and look at what happens if I make that surface a little smaller. And ask yourself what's happening to the charge inside of it. And hopefully it's obvious that there's less charge in it now. If I make the surface larger, there's more charge. Smaller, less charge. So it's very important to notice at this point that the charge inside of there is a function of its radius. It's going to vary with the radius of the Gaussian surface. All right. Next, we write out Gauss's law. Now, Gauss's law takes two different mathematical forms. I'm going to write out both, right? Because I teach both the college physics and the calculus-based physics. So, in the calculus-based physics, this is how we write out Gauss's law: that the total electric flux through any surface, which is the integral E dot dA over the entire surface, is equal to 4 pi k times the charge inside the surface. Right? This is basically equivalent to the algebraic expression for it, which I'm going to write out now. In my college physics class, I usually write this like the following: the sum, let me write that a little better. The sum of all the EA cosine theta terms over the surface is equal to 4 pi k times the charge inside the surface. All right, so these are equivalent expressions, really. All right. Which one you write out whichever one you're most comfortable with. All right, the next step now when you're dealing with Gauss's law is to investigate the relationship between the E and the dA vector. Right? Remember that the dA vector takes the direction of the normal. Usually in the college physics class I just talk about investigating the angle between the electric field and the normal. So I'm going to go ahead and draw some normal vectors to my Gaussian surface. I'm going to draw one right here. And again, remember, these are unit normals. Maybe I'll draw one like this. Maybe down here. All right, maybe imagine one right here. It's kind of hard to draw this, but that makes a right angle to the surface. It's kind of like coming right out of the screen, right? How many you draw is kind of up to you. You draw however many you believe you have to draw, so that until you're convinced you know the angle between the normal and the electric field, right? Normals. Now I'm going to draw some electric field vectors. Now the important thing is that I draw those electric field vectors right at the same spot. So if I pick a spot like right here, due to the symmetry of the problem, the electric field vector should point radially outward, basically in the same direction as the normal. If I come up to this point, same thing. The electric field should point up due to the symmetry of the problem. Again, right here, the electric field should be something like this. Right here, something like this. So what I'm doing is I'm drawing an electric field vector at every location where I draw a normal vector. And there's an important realization we need to have. No matter where I draw the normal and where I draw the electric field vector, the angle between them is 0. Therefore, the E dot dA part is just equal to E times dA. Vector symbols are gone because I've done the dot product part. And the cosine theta part is 1 because the angle between them is 0. Right? Over here we're doing the same thing. The cosine theta, remember that in this form, the theta is between the normal and the electric field vector, which we just talked about being 0, the angle between them. Cosine of 0 is 1. So this is equal to the sum of all the EA cosine, or just EA terms, because the cosine of theta is 1. I think what I'll do is I'll go ahead and complete this, and then I'll go ahead and work the right-hand side, what it would look like. Right. So E times dA, vector symbols dropped because the dot product has been done. Right. And then 4 pi k times the charge inside the surface. I'll go ahead and think about that a little bit later. Right. Getting back to the integral. If I think about these different locations, like here, 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 if they are all the same distance from the center, then it stands to reason that the electric field magnitude should be the same by the symmetry of the problem, which means this electric field, this E, is constant on the integral and can come out in front. All right, next step, integral dA over the green surface. So the dAs, these are little areas. I could draw like a little tiny one here, a little dA. I could draw one right here, a little dA. A little dA. So these are just little pieces of area of that sphere. If we add up all the little dAs, what we get is the total area of the sphere. So this left-hand side ends up equaling E times 4 pi r squared. Again, it's important to note that that r is the radius of the Gaussian surface because this integral is over the green surface. Right. We got to start thinking about that charge now. The Q, the charge inside of the surface. So 4 pi k Q, 4 pi k Q, and I'm leaving myself a little room on purpose. All right, the charge inside the surface is going to depend on the charge density. We have a total charge Q spread throughout a volume of 4/3 pi big R cubed. It's important, we would want the entire radius, the large radius. We would then have to multiply that by the volume of the Gaussian surface, 4/3 pi little r cubed, to get the charge inside of that surface. So this is charge per unit volume times volume will give us the charge inside that surface. And it's not too tough to show that. Let's see, the 4/3 pi cancel, so we got big Q over little r cubed. I'm sorry, big Q over big R cubed times little r cubed. Right? And there's our Q inside the surface. Big Q over big R cubed times little r cubed. Okay. Next step is just to algebraically solve for the electric field strength. We can divide by a 4 pi r squared. 4 pi's are going to cancel. We're going to be left with KQ over big R cubed. And when we take R cubed and we're dividing by R squared, right, this will go away, leave us with R to the first power. So there's how the electric field varies with the radial coordinate there. It varies linearly with R. Now this is not yet an electric field vector because it doesn't have a direction. I can give it a direction by just attaching a unit vector in the r direction. So there's our electric field vector. Now, in this algebraic form, basically the same thing. It's really a very, very similar calculation, right? You're investigating the angle between the normal and the electric field. We drew some normal vectors, we drew some electric field vectors. Everywhere on that surface, the angle between them is 0, cosine of 0 is 1. So this is going to read sum over the surface of E times A, whoops, equals 4 pi k times the charge inside the surface. All right, same argument here. There's no reason to think the electric field varies over this green surface. Therefore, it is constant on the sum. So we can write this E times the sum over the surface of all the areas equals 4 pi k times charge inside the surface. And again, the sum over the surface of the area, little areas of the surface, gives the total area of the surface, 4 pi r squared. And the last step would be to find the charge inside of the surface. That's done exactly the same way. Total charge per unit volume times the volume of the Gaussian surface. So E times 4 pi r squared equals 4 pi k times the same Q. Big Q over big R cubed times little r cubed. Solve for this electric field, you get the same thing, including the direction. So it's the same problem, basically the same work, a little bit slightly different looking math, but that's about it. So that's how we apply Gauss's law inside of a surface with spherical symmetry. I'm going to check the length of this video here. It's at 11 minutes. I'm going to go ahead and pause this and talk about how to find the electric field outside of that surface here, but I'm going to clean my picture up a bit. Alright folks, I'm back, and what I did here is I got rid of a bunch of work I don't need anymore. I've taken my picture and I kind of centralized it a little bit more because I knew that we were going to be working outside of the surface now, and I knew I was going to need more room. Went ahead and left all the previous work in the previous Gaussian surface, and what I have done here is drawn a new surface. And again, this is a new Gaussian surface, and that Gaussian surface is outside of the sphere. And what we can do now is we can use that Gaussian surface to find an expression for the electric field outside the sphere. So we would start by writing out Gauss's law, which I have, and you would write it either in its integral form, or again I would call this the college physics form. It doesn't really matter which. Then, just like before, we would draw normal vectors. So I'm going to go ahead and draw a couple of normals. You know, you just draw them at various locations. I like to put them fairly arbitrary in positions. Again, that one's right angle, right angle, right angle. You draw however many you have to be convinced you know the direction between the normal and the electric field, right? Which again is the next step. We'll draw some electric field vectors now at the same locations. So there's an electric field vector. Again, from the symmetry of the problem, that electric field should be straight away from that charge, all right? The electric field there, again, straight away from this positive charge. Another one right here, straight away from this positive charge. Right? Then we take note that the angle between the electric field and the normal is 0 everywhere. So the E dot dA, which is magnitude of E, magnitude of dA, cosine of the angle between them. Well, again, the angle between them is 0, cosine of 0 is 1, so we just get E times dA. There's no reason for the electric field to vary on the surface of this sphere, so by the symmetry, the electric field should be able to come out in front of the integral. And then what we have is the electric field times the integral dA equals 4 pi k times charge inside the surface. And integral dA is just A, the area of the Gaussian surface, 4 pi r squared equals. And now while I'm at it, I'm going to go ahead and talk about this, the charge inside our surface. Now here, this one's quite a bit easier. If you imagine this surface getting a little smaller or a little bigger, the charge inside of it doesn't vary. whatever this charge is, all of it is inside that surface. So I'm just going to put big Q. We can now solve this for the electric field by dividing by 4 pi r squared. Let's see. And we get kq over r squared. Right? It's basically pretty much the same calculation using this form of Gauss's law, right? EA cosine theta. We evaluate theta everywhere, right? Right here, theta equals 0, theta equals 0, theta equals 0, right? Cosine of 0 is 1, so this becomes sum of all the electric field times area equals 4 pi k times charge inside the surface. The electric field is not changing no matter where I am on the surface. The symmetry of the problem tells me the electric field is constant, so this can come out in front. The sum of all the little areas on this surface gives the total area of the surface. 4 pi r squared equals 4 pi k times. And again, the charge inside the surface, this does not depend on what form we're using. Charge inside that second surface is big Q. We solve this for the electric field, and we get K big Q over r squared. Now, right now I have scalars. If I want to give it a direction, I'll just multiply by r hat direction. And what that means is if I pick a point in space, like right here, r hat means radially outward, unit vector radially outward. And that gives me the electric field direction. Hope this video helped demonstrate how to apply Gauss's law in cases of spherical symmetry. Have a great day.